All right, so continuing on with the 6-1 notes, we're going to start off with a review problem, and then we're going to springboard from there into some new stuff. Real simple question. It says, how do you determine the average value of a function on a certain interval? Average value, hopefully that rings a bell as the integral over the interval. So the average value of f on the interval a to b is just the integral from a to b of the function over the width of the interval, which is just going to be right endpoint minus left endpoint. Then in the next thing, and this is where we transition into the new stuff, it says simply isolate the definite integral in the equation that you just wrote. I don't feel like rewriting this whole thing. I'm just going to call, this is just some number. The average value of f on the interval, I'm just going to call that f of c. So when I plug in a certain x value, that'll give me the average height of the function on the interval. And then to isolate the integral, like they're asking us to, I would just simply have to multiply this b minus a onto the other side. And that gets rid of the b minus a over here. And we have a whole new theorem just from simply multiplying a denominator of a fraction off of the fraction. They call this the mean value theorem for integrals. Before we dealt with the mean value theorem when we were working with derivatives. That was where we said the toll booth velocity has to equal the radar gun velocity at some point for a continuous function. What the mean value theorem for integrals is saying, let's kind of draw this out in pictures. Let's say we have to estimate, I have the same curve here 3 times, we have to estimate the area under the curve of this graph using only one rectangle. This is very Atari. We had 1 pixel where computers now have thousands when I was a kid. Anyway, I'm gonna first draw in a left endpoint rectangle to approximate the area. So my rectangle immediately goes up to the top of the function and then over for the width of the interval. So this rectangle gives me an estimate, gives me an overestimate. If I draw in a right endpoint rectangle, my right endpoint is actually on the x-axis, so I don't really even have any height at all. I have an area of 0. Obviously, the true area of this shape is far greater than 0. So my estimate is a pretty dramatic underestimate. What the mean value theorem for integrals says is there has to be at least one point somewhere on this curve where the height of the curve, you could draw a rectangle through that intersection point, and the area of the rectangle would equal the true area underneath the curve. So we have sort of this Goldilocks and the 3 bears situation where this estimate was too big and this estimate was too small. But mean value theorem says if you find the right point on the curve and draw a rectangle through it, that you will find one that's just right. So the estimate equals the actual area. And that's what they're saying up here, is that at for some x value called c that's on the interval, the height of the function at that point times the width of the interval will give you the actual area under the curve. That's all MVTI is saying. So let's look at an example. We've got a function, we've got an interval. It says what values of x satisfy the MVTI. So MVTI says b minus a times f of c somewhere. This is what we're going to have to figure out, is that c value, is equal to the integral, I should say. I guess I can just plug in, this is from 1 to 3. That's the interval they're giving us, for 9 over x cubed. And I guess I could even plug in, Jesus Christ, okay. This is important stuff. B minus a I could plug in is 3 minus 1, that's going to be 2. So 2 times f of c is going to equal, when we integrate this thing, I'm going to pull the 9 out as a constant, and then I'm going to integrate x to the negative third. There. Integrating x to the negative third gives me x to the negative second over negative 2. I'm going to put the over negative 2 out front. And I'm going to put my limits of integration in. Now if I want to isolate the f of c, I can divide away the 2. So that's going to give me f of c is, when I divide by 2, this negative 9 halves will become a negative 9 fourths. By the way, this is going to be 1 over x squared. If I plug in 3, I get a ninth. If I plug in 1, I get 1. So I have negative 9 fourths times negative 8 ninths, because this is 9 ninths. The 9s go bye-bye. I get a 2 over 1. I guess I just get 2, because a negative times a negative gives me a positive 2. So now we have to figure out where this function height equals 2. To figure that out, I'm going to take the function 9 over x cubed, and I'm going to force it to equal 2, and I'm just going to do the algebra to figure out where that happens. So if I multiply both sides by x cubed, I get 9 equals 2x cubed. Divide by 2, you get 9 halves equals x cubed. So x is going to be the cube root of 9 halves, which my calculator is going to tell me that's about 1.65. So 1.65 is the c value that makes this theorem true. So let's look at that on the graph. Here is the interval that I care about. They're saying at 1.65 comma 2, that's the point where I could draw my rectangle in, and that the area of this rectangle would equal the area underneath this curve in total on the interval 1 to 3. All right, one last example on the back here. That's scratch paper. Okay. This is an old AP problem. We've got two particles. They give us a position function for each particle, and they ask us to write an expression that describes the distance between the two particles at any given time. Well, if I'm positioned 30 feet from a point, let's say I'm 30 feet from a wall, and someone else is 20 feet from the same wall, assuming we're on the same side of the wall, we could just subtract. We could subtract our positions from the wall. Mine would be 30, theirs would be 20. 30 minus 20 would give you 10 in between us. We're going to do kind of the same thing here. We could say the distance at time t, the distance between the two things, I guess, would equal P of t minus R of t. Just subtract the position functions. Now it's possible that you could get a negative value here if R of t were greater. So there's a very simple way to fix that, just by using absolute value. So that's all they're driving at there. Then it says write an expression that gives the average distance between the two particles on the interval. Well, this is the distance at any given time. To get the average distance, I would need to take the integral of the distance function divided by the interval. So I would get the integral of d of t on the interval 1 to pi, and I divide that by the width of the interval, pi minus 1. That's it. That's the expression. It says use a graphing calculator. At what time on that same interval is the distance between the two particles equal to the average distance on the same interval? So now I'm going to, on my calculator, actually have to type in specifically what P of t is, what R of t is. Here's how I'm going to do that. I'm going to let the first function go in for y sub 1. So I got 2 cosine of pi over 4 times, I'll call it x. Oops, you know what? I want that x in my parentheses. So I'm going to call it pi x over 4. And I'm also going to put my calculator in radians because I was doing something else. There's the first function, that's P of t. For R of t then, I'm going to call that x to the third minus 6x squared plus 9x plus 3. Then to actually evaluate that, so I need to evaluate this function now. So I'm just going to do this. In y3, I'm going to write the expression for d of t. I'm going to call it absolute value. So I'm going to go to math and then over to number. I'm going to do the absolute value of the top function minus the bottom function. And now I'm going to clear. I'm going to do second quit. I'm going to get to a clear command screen, and I'm going to actually do the integration. So I'm going to do the definite integral, the finite integral. That was y3 in my, I already have absolute value of y1 minus y2. I've already got a name for that. It's called y3. I'm going to integrate from, or in terms of x, because I typed x on my calculator, from 1 to pi. And then I'm going to divide that answer by, in parentheses, because there's 2 terms that I'm dividing by, pi minus 1. So the question becomes, when does d of t equal 4.968-ish? Well, to get that, I'm going to graph d of t. I'm going to turn off these first 2 functions, get on the equal sign and press enter. And then I'm going to graph 4.968 as a constant function. So there is d of t, the curve. Pretty soon we'll see a horizontal line come through for 4.968. And they intersect several times, but we need to be on the interval between 1 and pi. So I think that's going to be this one here, because this is 1, this is 2. It's right around 2. So I'm going to go to second calculate. I'm going to find that intersection point. It's going to ask me which 2 curves do you want. This is one of them, so I'm going to hit enter. This is the other one, so I'm going to hit enter again, and I'm just going to get close to the point that I'm trying to find and hit enter again. It should give me something between 1 and pi. It's about 2.022. Finally, we get to this last question about speed. Speed is related to velocity, but also often confused with velocity. Here's what I'm talking about. Say you've got a velocity curve. You've got one of 4 different things that could happen. You could have a velocity curve that's above the x-axis moving away from it, above the x-axis moving toward it, below the x-axis moving toward it, or below the x-axis moving away from it. The thing to keep in mind when I say that speed and velocity are related but different is that speed is the absolute value of velocity. Your speedometer in your car never is going to give you a negative reading. It doesn't care if you're moving toward home or away from home, whatever. It's always going to be a positive value because speed is an absolute value. Absolute value, remember, is distance from 0. Well, in these 4 graphs, 0 is the x-axis. So looking at each of these 4 situations, the absolute value of velocity here is increasing because as this graph moves on, it is getting further from 0, further from the x-axis. So in this case, we have speed is increasing. Here, even though the velocity is positive, the velocity is above the x-axis, or the t-axis. The graph is moving toward the t-axis, which means the absolute value, the speed, is decreasing. Same deal here. This is the one the AP test seems to love, because your velocity is clearly increasing. If this is the velocity graph, it's increasing. It's moving up. But this, if you look at it as an absolute value, it is approaching the x-axis. It is getting closer to 0, which means the speed is decreasing because the speed, the absolute value, is getting closer to the x-axis. They love this one because everyone wants to put speed is increasing because they think, oh, speed, velocity, same thing, increasing. But you'll obviously come up with the opposite answer because of the absolute value concept. Here, if this is a velocity graph, it's moving away from the x-axis, so speed is increasing because the absolute value of velocity is increasing. It's getting further from 0. They kind of love this one too. So how does that affect us with this specific question? Well, we need to figure out which one of these 4 situations we have going on with particle p. Now, the other danger we're going to run into is the function they're giving us for p is a position function. It's not a velocity function. So we've got to ask ourselves, is p prime, that's velocity, because p is a position function. So is its derivative positive or negative? That's the first question we want to ask ourselves. That's going to tell us if it's a positive, we'll be in one of these 2 situations. If it's a negative, we'll be in one of these 2 situations where the velocity is below the x-axis. We can have our calculator find this for us if we want, or we can just differentiate it by hand because we're going to need the second derivative eventually anyway. P prime, let's see, we have to differentiate 2 cosine pi over t times 4. Differentiating that, the 2 can stay. Differentiating cosine gives you negative sine of the same angle. And then you have to chain on the derivative of the angle, which is just pi over 4. So that means p prime at 3 is going to be, let's see, if I multiply these constants, I get negative pi over 2. And then if I plug 3 in here, 3 pi over 4 puts you in the second quadrant. Sine is positive. in the second quadrant. I don't really care what the specific value is. I just care if I'm positive or negative. If I have a negative pi over 2 times a positive number, I'm going to get a negative result. So what that means is I've got either this situation or this situation, because my P prime is my velocity. P is the position, P prime is the velocity. I have to have one of these two scenarios going on. So then P double prime, let's figure out what that is. If P prime is negative pi over 2 times sine of pi over 4t, then P double prime, I'm eventually going to have to chain on another pi over 4. So I'm going to get like negative pi squared over 8 for my constant. And then differentiating sine gives me positive cosine of pi over 4t. So P double prime of 3 is going to be a negative number for this. And then cosine at 3 pi over 4 in the second quadrant is going to be a negative value. It's a negative square root of 2 over 2. And that's going to be a negative result as well. No, it's not. It's going to be positive. We have a negative times a negative. So what that tells us, between P prime being negative, that's one of these, and P double prime being positive, that's this one, is that the speed is decreasing because the absolute value of velocity is getting closer to 0. So if I'm going to write this nice and tidy for my answer, I'm going to say something like P is speeding up. Nope. My goodness. P is slowing down at t equals 3 because P prime of 3 is negative and P double prime of 3 is positive. And in general, that's how you can tackle any question that involves speed. Figure out if the velocity is above or below the x-axis, and then figure out if the velocity is increasing or decreasing. Put those two things together to give you one of these 4 situations and just sort of interpret the result. If you're getting closer to the x-axis, like we are here, that means you're slowing down.